Herbert Spohn giving this set of lectures. Herbert will talk about hydrodynamics of lattice gases, and so I think we can start here.
So thank you very much for this kind invitation here to the Raman Institute. I mean, I have been several times in Bangalore, but I don't think I have ever been at the Raman Institute, so I'm very happy to lecture here. Welcome, everyone. And so let me just put my name here. And I'm from the Technical University in Munich. So is this somehow visible? I'm in this size, or okay? Okay, so I'm one of these old-fashioned people who still like to work on the blackboard. I mean, so most of my things will be written here. And of course, I mean, you know, as mentioned already, I mean, perfectly welcome to ask questions during the lectures, and you know, the more discussion, the better. And so, the lectures which I was planning is the hydrodynamics, and I put actually, you know, the full title would be to add the term stochastic lattice gases. And since this is a school on statistical physics, maybe I have a lot of time. I mean, maybe you give me sort of a few moments to give sort of just a general broad overview, you know, where this kind of topic is actually located. And so first of all, you know, it's all statistical physics, but very naturally, statistical physics, you have to tell me, you see, at some point, presumably, I'm going low, and then you cannot see anymore. I mean, so I'm trying to, okay, anyway. So, of course, you can divide this into equilibrium and non-equilibrium. And so this will be static, and this will be dynamic. Okay, and the lectures, I mean, as you can see from the title, I mean, I talk about hydrodynamics, so it will be a dynamical problem which I'm going to study. So I'm sitting in this corner. Now, the first thing I want to sort of remind you is that, you know, while this is a very traditional separation, actually it's not completely clear. Static just means that sort of, at least on a macroscopic scale, nothing is really moving. And of course, you can also produce non-equilibrium situations where nothing is moving. I mean, these are the so-called, I mean, we like to call them NES. I mean, so this is just a abbreviation for non-equilibrium steady states. And of course, you know, it's very easy to generate them. I mean, for instance, I mean, sort of one of the canonical cases is that I'm sort of trying not to get too low, so let me put this picture up here. I mean, imagine that you have a system, and then you put one temperature over here, another temperature over here, and if you make this temperature different, I mean, then you will induce an energy flux. And of course, if you wait it long enough, and if you sort of make sure that, you know, these reservoirs are actually correctly, you know, at given temperature, so I mean, that of course you have to maintain, but you can maintain this over a long time, then you will induce, and eventually it will come to a situation where on the macroscopic scale nothing is changing. But so you've reached a steady state. I mean, so you might think that you are in a static situation. But in order to figure out what that steady state is, you have actually, you know, to solve some sort of dynamical equations. And so it's one of the, you know, sort of big miracle of statistical mechanics. And if you think about it, of course, historically, you know, I mean, I think, you know, this was sort of a very important step, is that somehow when we look at the states which we call equilibrium, you don't have to worry about any dynamics. You know, once you say the system has, for some reason, reached a particular thermal equilibrium situation, not a NES, then, all what you have to do is you can more or less write down immediately, sort of some Gibbs formula. You can write down what is the formula for the state, so some quantum mechanically, sort of thermal equilibrium density matrix, and then you can work, and you don't have to worry about the dynamics at all. Okay? Anyway, so I'm in this situation over here, and the next distinction which I would like to make is that we can look at various systems. I mean, of course, we can look at quantum. So this basically means that you have a time evolution which is unitary. And we can also look at classical. So, this, of course, Newton's equation of motion. So let me just call it deterministic dynamics. I mean, dynamics which you obtained by solving deterministic evolution equations. So you might think, I mean, what is specific about this distinction in terms of statistical physics? Of course, the most important thing is that we want to understand, I mean, in particular here in this non-equilibrium situation, we want to understand this with random initial data. That sort of makes the statistical mechanics random initial data. Okay, these data could be either equilibrium, then of course we don't have to worry so much about the dynamics. We can study directly the state, or it really involves time evolution, and then of course we have to solve either the unitary dynamics or the deterministic dynamics. Now, when you look at the history of statistical physics, this is not really all. Of course, I mean, this is what you teach your students, and I think it's certainly a very sensible way of making a distinction, and depending on the situation, I mean, typically, you in your course you carefully divide, but clearly there are, many systems which, of course, quantum theory is sort of more basic, but still there are many systems where the classical description is still valid, and so this is, but what actually, a large part, or let's say a substantial part of statistical physics is actually concerned with stochastic modeling, right? I mean, if you think about, the way how we do statistical physics, of course, this microscopic, I mean, this underlying sort of atomistic or microscopic dynamics is, of course, very crucial framework in order to do the modeling. The modeling is not totally arbitrary. But very often these problems are simply way too difficult, way too detailed, and we have to resort to sort of a more sort of, a somewhat more modest approach where we sort of guess a good statistical model and then we analyze that model, okay? And so let me just call here as a third area, which is called, which I just want to call stochastic models. They're of course not totally arbitrary at all, right? But it's important, that this is also part of statistical physics. Now, when you look at textbooks, I mean, most textbooks, of course, they are either concerned with this part or equilibrium or maybe non-equilibrium. But there's one textbook. In fact, I prepared a list of literature. I mean, this we could at some point we can somehow put on the net, or I can show you. There's a very nice book by Sid Redner and two other co-authors. So let me just put here Sid Redner, which is really a textbook, and it's called Statistical Mechanics from a Kinetic Point of View. And so he emphasizes very much this kind of stochastic modeling, and in a sort of textbook version explain many of the kind of things, and I think it's a very useful and I think almost necessary book in order to sort of see that this part is really an integral part of statistical mechanics. So from what I'm saying, it's this part which I'm going to focus on. Okay. Now there are, of course, a very famous example. I mean, so maybe I give you two examples of early examples of stochastic modelings. So first of all, there's a famous Einstein paper in 1905. And what he realized is that when you look at the tracer particle in a fluid, which people could sort of actually even at that time they could see under the microscope. You see, it's sort of course it's rather small, but if you magnify, I mean, then you can sort of it's somewhat larger than all the fluid particles, and so you can actually see. And what you observe, of course, is sort of there's a book by Perron which sort of produces these figures. I mean, it's quite amazing that he sort of in the book he presents. I mean, this trajectory which he has seen under the microscope, and you see sort of like random trajectories, and once in a while, I mean, there's a collision, and so these are pictures which he's drawing. And what Einstein understood is that these trajectories are sort of still complicated, and you don't really know how to describe them. And he realized that modeling this as random walks, and then sort of understanding that the random walk on large scales looks like Brownian motion. He had a good statistical model in order to describe the system. Of course, it was extremely important for many reasons, which I don't want to go into, and presumably you all know. But in any case, I just want to emphasize that there are famous examples of this modeling. Another case which sort of came to my mind is when you look at the Bohr atom. So you see, I mean, you have here maybe the energy, and you have here sort of a few energy levels like this. And what Bohr was saying is that once in a while, I mean, the system just jumps maybe from this energy level to this one, or maybe it jumps down from this one over here, etc. Right? Now, of course, maybe he didn't express it so clearly at the time, but that's of course the stochastic modeling. And in fact, I mean, and nowadays, I mean, sometimes people sort of worry about our random number generators, and people do use, I mean, even commercially do use sort of quantum mechanical effects to produce, even more perfect random number generators than what you could use otherwise. I mean, the usual thing is to take dynamical systems which sort of, are chaotic, and this sort of produces for you sufficiently sort of quasi-randomness, but even more, okay? And so you see that this idea of stochastic modeling has a long history and is very much widespread. Now, the main part of my lectures is that, this, or in my language, I mean, this would be one-body problems. And I mean, it's either this energy transitions in an atom, or maybe Brownian motion, or you can think of many other, there's a whole sort of area which is called stochastic thermodynamics, which looks at few particles, stochastic thermodynamics, and so this is fine. I mean, but sort of the focus of my lecture is that actually I want to study many body systems. Okay, so these stochastic lattice gases are one example. So, just to give you a picture of what they look like is that, I mean, maybe you put some underlying lattice, and then on this lattice, I mean, you have sort of particles sitting, and they maybe they can hop to neighboring sites, and of course they interact in the sense that, I mean, this jump rate will depend on what is the local environment. Or maybe you can just put, just the exclusion rule that, I mean, if this particle wants to jump over here, it's not allowed, something like that, okay? But the important thing is that it will be many-body. And that sort of, gives you an interesting insight of course, also here on this side, I mean, when we do statistical mechanics, we have sort of many degrees of freedom in mind, and so, also on this side, of course, you have always large systems. And now I want to do the same thing, on the level of stochastic modeling. Now, of course, when you look, and presumably also at the later lectures, I mean, there will be many examples of these things, and which are sort of all of somewhat, different emphasis. But sort of for my lecture, it will be sort of, this is what I'm going to focus on. Okay. All right, so maybe I should sort of mentioned before going to this thing, just mention sort of two cases which I mean, just sort of tell you that this stochastic modeling is sort of quite widespread. I mean, so one obvious thing is where you use this modeling is when you look at colloidal suspensions. I mean, this is, so to speak, you know, the many particle problem of Einstein. Einstein, you know, if you have a very dilute density of displacer particles, I mean, then you can essentially ignore the interaction, and then you can sort of handle it, you know, according to what Einstein told us. But if you now look at the colloidal suspension, you have many particles sitting in a fluid, and of course, then there will be important interaction effects. And so I'm not going to study this system at all, but you know, this would be one typical system where you really need a many-body theory in order to understand what's going on. Another thing which, again, I don't want to study, I just sort of want to sort of, you know, two examples which came to my mind. I mean, so you can look at something which is called active matter, you know, which of course is a whole area by itself, and I'm far from, you know, just observer. I don't know anything so much about this subject, but the point is that you know, you look at you look at many objects, but they're not just your sort of particles, or like in this stochastic model, you know, where these particles which are jumping don't have any internal degrees of freedoms, but you know, I mean, active means that they are sort of content of objects, you know, which have their own energy. You know, the interaction between these objects are sort of, you know, very different from what we would learn from objects in sort of more mechanical models. So here, I mean, you know, I mean, at least to me, the famous example are these bird flocks. So, you know, you have many birds which you can see on the sky, and you know, they form beautiful patterns, and you wonder where do these patterns actually come from? And now, if you sort of, you know, are interested and you want to do sort of make a model of this, of course, you know, you have many birds, but then the issue, how do you model the interaction between these birds? And then for this, typically, you know, of course, again, you know, I mean, you have to insert rather special things. I mean, you cannot use just, you know, a simple model like this, but it's again sort of an example of stochastic modeling, right? Okay, so let's see what else I want to say here. Okay, so that's I guess this part. Okay, so now I told you a little bit, you know, sort of somehow in the direction which I will be going, and the next question is, you know, I mean, just like here we have unitary and we have sort of Newton's equation of motion. I mean, there must be also some guiding principle over here, and one of the guiding principles is that we want to use it's evolutions which are called Markovian. I mean, you know, for any real systems, I mean, this will be an approximation, presumably. I mean, just like in the Bohr atom, I mean, you know, when you, of course, Bohr just postulated as a phenomenological model, then later on people realized that if you couple the atom to the quantized radiation field, I mean, then you can understand these kind of transitions on the basis of a more unitary model. And when you then start computing, you know, this transition and how long, you know, sort of the waiting times of these transitions, then you realize that you know, the true model, you know, would deviate from the Markovian model. But the Markovian model is something which is, you know, very widely used, and you know, it's a major simplification. So let me just say one word about this in generality. So what does Markovian mean? Well, okay, so you have you know, something some evolution in time. A moment sort of, it's not really specified, but what you want to sort of do is that you want to divide it. I mean, so, you know, imagine that up here you have your states, which is sort of a little bit vague. I mean, this will become clearer later on. Anyway, so here you have this time, I mean, which I call now. And then you have the past, and then you have the future. Now, if you think about mechanical systems, if I give you the state now, then of course, you can put your unitary time evolution forwards in time, and you can put the unitary evolution always also backwards in time. And so, once you have specified now, so to speak, the future and the past are actually determined. Now here, for stochastic system, this cannot be, because, after all, as I evolve in time, there will be randomness, and so it's not determined. However, what happens is that if you condition on now, so condition just means that you're fixing, the exact state at time t at this particular time, which I call now. Then the past and the future is stochastically independent, so it has a product structure. Okay. So this means that whenever you want to do any kind of average and expectation in the future, you don't have to worry about the past anymore, given that I specified the now. Past and future are independent. Okay, and this is when Bohr wrote down his model, I mean, of course he didn't say it, but when you look at it and with modern eyes, I mean, what he was saying is that when you look at this point and you ask yourself, how long will it take to make this transition, then what he implicitly assumed is that you have a waiting time which is exponentially distributed, right? I mean, that's sort of radioactive decay. I mean, it's an exponential distribution, and of course it's not totally obvious, but when you sort of think about this a little bit more carefully, then you realize that this exponential distribution just means, or can be translated into this kind of picture. It's a Markovian assumption. If you take some other waiting time, it will be, which you could do, but then of course life becomes much more complicated. Then you will lose this particular Markov property. Okay. So of course, I mean, the kind of dynamics which I'm using, I mean, they have names, so let me put them also here. I mean, so in some cases they are called Glauber dynamics. I mean, just that you heard these names, I mean, I'm not doing something which is sort of very original here at that stage. It's the Kawasaki, but Kawasaki. So this is typically Glauber dynamics is sort of used when there are no sort of extra conservation laws. The Kawasaki is used when there is a conservation law. So I will be mostly actually talking on this level because these particles are jumping, and so the number of particles actually will be conserved. And but the point is that and this will be explained sort of in great detail, is that I sort of want to also study non-equilibrium situations like this one, right? I mean, so maybe Glauber dynamics is very often understood only in terms of equilibrium dynamics, but so let me just put here sort of it's a non-equilibrium version of these things, right? Okay, very good. Okay, and then one other thing which I have here in my notes, maybe because Markovian. So the models which I'm going to use and which is sort of for theoretical purposes convenient is that the states. So if I specify what is the complete actual state of the system, they will be discrete. Like these sites which are either occupied or empty. And maybe I have a huge number of them, but it will be just sort of a discrete set. But for the time, I'm still going to work with continuous time. I mean, that's just it's a theoretical construction, but many of the computations which you do would either impossible or would become much more complicated if I don't use continuous time. And of course, if you do numerical simulations, which in many of these systems people of course have done and do nowadays, and it's an important tool to understand beyond doing theory. It's a very important tool to understand such kind of stochastic models, And then on the computer, well, in principle, of course, you could also do continuous time, but this is sort of typically a little bit sort of complicated. And so what people do is actually, you also discretize time, and then it's sort of what people call a Markov chain. I mean, chain just means that the state space, I mean, it's sort of, it's always, everything is discrete. Space is discrete and time is discrete, okay? So maybe I should put this here. Well, okay, it will come anyhow. All right, so any questions at that stage? Okay, so what I'm going to do is I will first sort of, otherwise you cannot do any computation at all. I will sort of go a little bit into describing this kind of stochastic processes which are behind these models. And this I will just do with, now maybe some of you have heard these kind of things, but nevertheless, I mean, let me do it anyhow. So I will first do this, in the case of a finite state space, and give you some of the basic formulas. Once we have done that, then I will go, the way how it's constructed, that I will go into sort of various typical examples where on one side, there's some interesting theory behind and also some interesting physical phenomena. Okay, so that's somehow, and rather than writing you down the list of what I'm going to do, I think that that's sort of just a waste of time. So let me just start right away with the first thing which I want to do, which is chapter 2 already. And this I'm worried that everybody knows already, but you will see that I maybe emphasize things which are not so well known. Markov-Chain processes. Okay, so this is a little bit probabilistic, and I guess the first part, let's see, maybe I should say what I did. The second part. Okay. Okay, so there are two parts. I mean, so one of them is sort of just a general structure. And the second part will be, I'm coming back to this distinction over here. I mean, once I'm on that leveling, on the level of modeling, you still would think that I should not have lost, the distinction between equilibrium and non-equilibrium. And you will see that on the level of these Markov-Chain processes, there's a very clear and simple distinction. And so this is sort of the second part of this section. Okay, so what do I do? Well, I mean, first of all, I take a finite state space. So these are just labels. I mean, so 1, etc., all the way up to kappa. Okay, which I can think of some points here. I mean, this, and then they have some label, right? Okay, now eventually, you see, we want to study systems of this type, and then when you take, let's say, you take some volume, some finite volume, some box, let's say, which is in the d-dimensional lattice. Okay, I mean, so some section like here, and then you ask you the number of states. I mean, then I have, I can, let's say I do the exclusion rule. I mean, then I have either one particle or no particle, and so the number, so the kappa would be equal to the power of lambda, right? And even if you make lambda rather small, I mean, this is a huge number. Okay, so this is the many-body problem. I mean. I do as if it's a finite state space. That's fine, but eventually, if the number of states is huge as this one, you have to sort of think about other strategies, right? But still, it's like telling the people, you first do Newtonian dynamics, sort of, quite in general, but then later on, I mean, you have to do something else in order to deal with the large number of particles, right? Okay, so let me first do this, and now the Markov-Chain process means that you sort of have chums let's say you go from this one to this one, or maybe you go from this one to this one. And for each of these jumps, I mean, you specify a jump rate. So this is C from I to J. So this is directed. I mean, this is maybe I, and this is J. And of course, you know, I will never sort of write this error. It's just sort of a matrix, if you want. So, and I write this Cij. Now, in order to qualify as a jump rate, it should be positive. And you know, sometimes I include the 0. It's just for notational purpose. You see, there might be no jump possible from here to here. That just means that the weight is simply to 0, right? I mean, so that's what I do. And now the point is that once I give you the jump rates, it's sort of like giving the Hamiltonian. Once I give you the jump rates, everything else is determined. And so I have to go through these few steps in order to tell you, you know, what is actually, in what sense this stochastic process is determined. So let's first make a picture of the evolution. So the evolution is quite simple, right? I mean, so you have time t here, and maybe you start with some initial state. So this okay. So I guess I mean this set I call omega, just a set of states, and so here I have plotted, so to speak, the omega states, right? I mean that's it's completely general, right? I mean you know, I just, you know, the labeling is of no importance. I mean, I just have to give these labeled points. Okay, and so I start with some particular state, and then I stay there for a certain time. But the main point is that this time will be now random. Okay, so all these random times, in order to have the Markov evolution, will be exponential. So we're going to write down the formula in a second, but the main point is that this is a random time, and then you know, it does a jump, I mean, to some other value over here, so it does jump over here, and then you stay for another random time here, and then maybe you jump to this state, etc., right? So this is what is called Markov jump process. Okay, and now I have to tell you what the probabilities are. It's just sort of like explaining to somebody, you know, throwing the dice. I mean, what is it probabilistically, right? I mean, then you tell them, you randomly pick a number between 1 and 6, and then you repeat independently these kind of things. So I'm just doing exactly the same thing on that level. Okay. All right, and so maybe in fact the omega might be not such a good thing. I mean, so let me call this sort of, you know, the x of t. I mean, it's sort of like a random trajectory, which of course takes points in my space omega. The x of t is this curve here, but you know, the values which this curve can take must be between 1 and kappa. Okay, so now let me do that. I mean, so first of all, I have to do the total weight Ri, which is the sum j equal 1 up to kappa of the final points. And this, of course, is something which is, well, let's say I assume that this is larger than 0. So at least one of the weights has to be different 0. Otherwise, I cannot jump it on. Okay, and then the waiting time. So let's say this is I here, state I. So this will be the waiting time, right? I mean, so just asking, you know, how long do I wait? And this I do exponential, and the weight, of course, is Ri. So it's e to the minus Ri times t. Now I can do a jump only if this happens to be positive. So let me put here t larger or equal to 0. And of course, later on I don't do it, but here for the first thing I should do it is that, you know, it's sort of a density, but it's a density relative to what? Well, it's just the usual volume measure, so it's relative to dt. So when I do integrals, I mean, it's always this continuous time. Okay? But now you see this is not quite right because, you know, it has to be a probability distribution, so it has to be normalized to 1. And so if I normalize this to 1, I have to put the Ri in front. All right. So when I now do the integral from 0 up to infinity, this will be equal to 1. Okay, so now I know what happens, you know, for that period of time, and then I'm just, throwing an exponentially distributed random variable, and whatever that particular value is, at that time I do the next jump. But now the question is, what will be the next jump? Okay, so this was one thing. And then there must be a jump. So now this state is what I call J. This is where I jump to. And well, I mean, the jump is, of course, according to these weights, but you see these weights are not normalized. I mean, so I have to sort of first normalize by the total weight. And so the jump will be 1 over Ri times C of Ij. So to speak, the normalized weight. You see, this must be a probability distribution. And so that's, of course, greater or equal to 0. And if I do the sum over if I do the sum over all j from 1 up to kappa of this 1 over Ri, let's put it outside, 1 over Ri Cij, this is just equal to 1, right, by construction, right? Because this sum is Ri, and so I divide, so it's just a normalization, okay? So this will be my jump probability, and then I just continue. I mean, so now I have another exponential. It's all independent. I have another exponentially distributed random variable, and I wait for a particular random time, and after I have this time, then I pick another random variable, all independently, which is now takes discrete values and which has these probabilities, etc., etc. Okay. And so let me just write down sort of one formula for you that you can understand how this works. I need this formula for another purpose. And so let me just write down this formula. So now I want to write down the formula for this probability, for this path. But now, of course, the path will have many jumps, and so let me sort of tell you how this works. I mean, so I have I naught, which is my initial state. I mean, that's times 0, and this is maybe In, so that's the final initial, and that's the final one. So I have n jumps, final. I have n jumps altogether, and so if I make now a plot. So I have here maybe my T1, and then I have here the T2, etc. Right? And now I have just to follow this kind of prescription. I mean, I do the first jump from I0 to I1. And that's I0, then comes the next state is I1. So they're completely arbitrary. But you see, it's a probability. So I have to divide it by 1 over I0, right? Of the initial state. Okay, and now I do the waiting time. So this one is my waiting time. T is T1. So I have Ri0 e to the minus Ri0 times Ri0 times T1. That's the first one. Okay, and now I just keep going. So this is the first jump. This is the first waiting time, second jump, etc. So the last thing in my formula, which I'm just not going to write out, everything in complete detail will be the weight of n minus 1, and then there will be the time Tn, and of course I have so to speak the a priori measure, which is given by this product of the dt1 up to dtn. Okay, so here you just sort of copy this thing, and now you observe sort of a nice simplification, namely. You can simply cancel this, and so the actual formula which you write down for the probability of a particular trajectory is actually simply this kind of multiplication. I take the weight from I0 to I1, then I take this exponential factor, etc., etc. Then I have the weight here from In minus 1 to In, and then I have the weight of the final time. So the last time is here. Was In, and this last step is Tn. Okay. So now I've written down you for the probability, and the point is now everything is fixed, right? I mean, so I've given you the weights, and in terms of the weights, I constructed this jump process, And that's all what I have. Now, of course, this is an extremely detailed information. I give you the probability of all possible paths. And that's something, it's just like in statistical mechanics. I mean, if I give you position of all particles, I mean, what do you do with it, right? So here you have lots of, even if I have a finite state space, I mean, you have sort of, a huge number of possible paths, and so which one to take. So clearly, you must sort of get to some reduced description, which is something which you want to maybe, analyze and which contains your physical information. So there is reduced description. Okay, so this basically means, you have some observables and you want to compute expectation of these observables. I mean, that's sort of what I roughly mean by reduced description, right? And so let me do one important observable which people like to do in this context, which is a transition probability. So what is the transition probability? Well, I mean, you ask yourself, what is the probability that I start, let's say, in the state I at time t equals 0, so this is time here, and I arrive at state j at time t. This would be the transition probability. Average transition probability, so which of course is a much reduced information, right? And so what do I have to do for this? Well, I mean, you have to do an average. You have to do an average, but you have to maintain, sort of the data which are given here, right? I mean, so in particular, you want to have that the total times add up to t. I mean, so you have a delta j equal 1 up to n, tn should be equal to t. Okay, and then I'm not going to write out everything. I mean, you will have the information that I start at I have the information that I start at j. So you want to, and then you want to do a sum over many things, right? I mean, you want to, in particular, sum over n. So n is here the number of jumps. And then, of course, you want to integrate over all these waiting times, and so it's an average of this object here, but it's sort of a restricted average over that kind of constraints, right? And because this is all what you want to know. Okay, so now this looks like a horrendous problem, which you don't really know how to do, but fortunately, and that's part of the Markov properties. Fortunately, there's a simple formula how you can do that, and so let me just explain this for you. So I first have to introduce two matrices. So I call L naught. No, I call. Let's see. How did I want to do that? Yeah. Okay. Okay. So I want to introduce two matrices. One is a diagonal. Okay. I introduce a matrix L. Okay. So it's a kappa cross kappa matrix, right? So in the case of system which I'm interested in, there's of course a huge matrix, but here we just have a finite matrix, and so let me call this matrix L, and it's defined that by the diagonal terms I take minus the Ri. The Ri are these objects which are defined right over here. Okay. Right, and then I want to take off diagonal matrix elements. Lij, which are equal to the Cij. Okay, so this matrix, maybe I draw here. So on the diagonal, you have the minus Rj, and here the off diagonals, you have the Cij. And now I want to sort of give two names to this. So the diagonal part I want to call L0, and the off diagonal part I want to call L1. So the diagonal part is just sort of this matrix where I put all the matrix elements out here 0, and along the diagonal just the negative of the total weights, and the L1 are just all the off diagonal matrix elements. I mean, these matrices, I mean, just those people who were taught, know about quantum mechanics, these matrices are not symmetric generically. Well, they're in some sense never symmetric, because you know, it makes a difference whether I jump from I to j or from j to I. All right. All right, so now, once I have this, I mean, then I can do this complicated computation. And what I have to remind you is something which one should know, but you know, maybe you have forgotten already. So I want to compute the exponential of this matrix. So I want to compute e to the LT. And I want to do this in terms of time-dependent perturbation series, in the sense that, you know, I put the diagonal part upstairs, and the off-diagonal part I put downstairs, okay? And so I write this as e to the L0 at time t plus an integral from 0 up to 1, 0 up to t, dt1. And now I have e to the L0 t minus t1. So t1 is, so to speak, the jump time. And then I have here the L1. And then I have e to the L0 t1. And I do, okay, so I sum over all, and it's an infinite sum, right? I mean, this corresponds to 1 jump, 2 jumps, 3 jumps, etc. So I can have arbitrary number of jumps, so I have to take this infinite series, right? So this is what you call a time-dependent perturbation series in quantum mechanics. Yes, question?
So when you assume that LI is minus RI.
Why do I assume that?
Yeah, when you did assume that.
Well, I mean, okay, you see, I want to, so now I erased already an important formula. Okay, so that sort of happens. But you see, I mean, in my formula, here it's still standing. You know, in my formula, I have appearing e to the minus Ri times t. And so, this is exactly the e to the L0 t, if you think about it, right? I mean, so this is why it appears.
Yeah, so I was asking, does it put a constraint on the systems that you are modeling? Because it would mean that the system never stays in that state for like forever. Like it,
No,
because it kind of assumes that you cannot, I mean, there is no state from which the system does not jump away from. Like if you wait long enough, the system always changes.
No, at the moment, I'm not waiting at all. I mean, I'm just, I just wanted to as my first exercise, you know, in terms of reduced description, I just wanted to determine what is the probability to go from state I to state j in the time t.
And
everything else will come later, but
okay.
I'm just doing this exercise for you.
Mm-hmm. Okay.
Okay.
Mm-hmm.
All right. So let me just sort of finish the exercise. Maybe I can come back to your question. So first, I this is just a complete algebraic identity. I mean, there's nothing deep behind it. I mean, so if I want to compute, so the L, maybe I didn't say this. I mean, the L is of course L0 plus L1, right? All right. Okay. I have this infinite sum. Okay, and then now I compare it to with the probability which I had, and you see that when I really work out this matrix element, so now I want to take of this thing the matrix element ij, and of this whole sum I also want to take the matrix element ij. And now when you look at this thing, I mean, you see it's exactly this kind of thing which I wrote down. I mean, what I've written down here, you know, the nth term is simply n jumps, right? So let me just do this exercise in the lowest case. I mean, you know, here it's L naught. I mean, just I take the matrix element ij. It's diagonal, and so here I just have no jump at all. I'm just sort of waiting. It's just e to the minus rj times t, right? And then you do the first jump. I mean, so you know, things are properly normalized. I mean, this is what I told you already. So I verbally I omit this. I mean, so here is sort of your waiting time, which is still remaining, and then you know, this is the waiting time for the first. Okay, so what I'm plotting here is sort of you have a first jump from here. With so this is t, this is T1, and that's T minus T1, right? And so maybe I should read from here. So first, you know, I do the T1, and then you know, I do this transition, and well, like actually I wrote it in a different way, but it's not important. I mean, so you can sort of figure out that I do the indices correct here, and so you see this corresponds just to the first term, and then you do the second, etc., etc. Okay, and so you see that I get this nice formula that if I want to do the transition probability from I0 to JT, then this is nothing else but exponentiating that matrix, and then I have to take the IJ matrix elements. Okay. All right, so maybe that's something sort of which you have to think about a little bit further, but you know, this is sort of part of the simplification of the Markov approximation that you know, some of these probabilities, I mean, not all, you see, there are many other probabilities you could ask. I mean, you could ask, for instance, I take a state I and I take a state J. How long do I have to wait until I first reach the state J, right? I mean, that would be a more complicated I mean, maybe not more complicated, but a different, maybe interesting information. And then I would have to rethink of how to actually do that. You see, but I have the basic formula. So from that, you know, everything somehow has to follow. In some cases, maybe the things are very difficult. I don't know how to do the computation, but you know, at least in principle, you know, everything has to come from the sort of master formula, which tells me what is the probability of particular trajectories. Okay. All right. So now we have done this thing, and so let me just sort of tell you a few things which you can do with it. So first of all, I mean, I mean, the L is the backward generator. I mean, this is what called people the backward generator. Well, there must be another generator which is the transpose of this, and this will be the forward generator. And so let me just explain you what is the difference. And the point is that L is something which acts on observables, and LT is something which acts on probability distributions. And so since this is an important distinction, let me sort of explain this to you. So maybe I have some function on, so now I look at some observable. And of course, you know, observable is sort of a somewhat vague meaning. It could mean many things, but here for that instance, I mean, I'm thinking of some function f which is defined on omega, and let's say it takes real values, right? I mean, so it's just a function on my finite state space. And maybe what I would like to compute is I would like to compute the average value of this function at time t. So xt is simply, you know, the position of my Markov jump process at that particular time t, which is of course a random quantity. I mean, it's sort of according to the randomness which I defined. So I want to do the average over all paths, but I want to sort of maintain one information, namely I want to maintain that at time t equals 0, I start at I. So this is the starting point. Okay. Well, now if you look at this, I mean, it's clear that you know, this quantity I can express through this transition probability. So I can okay. So I have to go here. So this is equal to the probability starting at I equal to 0, and then going to the point j at time t. And at time 2, I just do the average. I mean, so this is f of j, and then I'm doing this summation over j 1 up to kappa, right? I mean, so once I know the transition probability, I can compute such expectations. But then you see that this is nothing else but e to the, I mean, because the transition probability is given by the exponential of the backward. You see that you know, this is, I'm just inserting what I found over here, and then I'm explicitly doing the sum over j, and so this is okay. This is a vector. So this is a matrix, and so I take the ith entry of this vector, right? So it's just linear algebra. Okay. All right. So this is now I can also look at probabilities. Maybe I put a little bit more space here. I can look at probabilities. So, for instance, I can say, okay, I have some probability at time t equals 0. So I give myself the probability distribution at the initial time. So I have my initial probability. I call this ρi. So it just tells me that I start initially not at the fixed state, which was sort of the point over here, but I imagine that I have some probability distribution. So these, of course, are probabilities. So y has to be equal to 1. Okay, and then the question is, what is the probability distribution at time t, right? So that's maybe something which I want to know. And of course, that's again now easy to do. I mean, so this is the rho j at time t. At time t. Well, I mean, this is just the summation of I going from 1 up to kappa. And then I have here my initial probability distribution, which was the rho I. Then I use the transition probability, which goes from I0 up to jt. And that's already the answer, right? I mean, so, as a function of j, I mean, this will be a probability, and so this is just nothing else but the probability distribution at time t. And so you see, in terms of this generator, I can write this as e to the lt, but now I have to be a little bit careful. Namely, it's ij, and then I have the rho I sitting over here, and it's a summation I over 1 up to kappa. And so you see, it's more convenient to define the transpose because I'm sort of acting backwards on this one. And if I would do the transpose, then I'm interchanging these two matrix elements. Then I get the forward, and so I can write this as e to the transpose of t of a. Okay, so this is this fine distinction between L and its transpose. The transpose is acting on probability distribution, and the L itself is acting on observables. Now, once I have that, I can write down what people call the master equations. You see, I just have to solve a linear evolution equation. I mean, so I have ddt of my observable is nothing else but L acting on F. And if I mean, this is at time t. Okay, this is at time t, and this is at time t. So I just have to solve this linear evolution problem. And if I want to do the probability distribution, then I have to take the transpose, and I get this thing. And so let me write out this one in full glory, so that you can see that I'm just doing what everybody else is doing also. But maybe people sort of do it more upside down. So if I just write out exactly what this transpose is, then you see that I have here the C, but now it's sort of inverted. I mean, ji, and then I have to act on rho j minus, and then it's Cij, and then I have to act on rho j, right? And so you see, it's this. I mean, here it doesn't make any. I mean, here since it's just sort of I'm doing the sum over this. Sorry, this is no. This is rho I. Okay. Okay, so you see, here I'm just summing over this. I mean, then it doesn't make sort of anyway. So this is what the formula is. But the important point is that I have to do this transposition here. And if you look at the many-body system, it's even doing this working out what the LT is might be actually quite complicated. And so when you do computations, and I will show you very soon sort of examples of that. When you do computation, you will see that it's much better to actually use the backward generator. And why is it so much better? Because you see here, I had already difficulties of writing it down, and you know, I have to be careful with doing these matrix elements. But if you write down the evolution equation for the, maybe you know, I should just sort of that people follow what I can say. I mean, you see, this is usually called the gain term. So these are all the transitions from J into the state I, and this sort of the loss term. And you know, very often people sort of write down this as a basic definition, but that's very misleading. I mean, the basic definition is what I told you at the beginning. I mean, I wait in a particular state for an exponential time, then I jump, and then I wait, and all these processes are called to sort of independent but prescribed probabilities once I give you the weights. But when you actually work out what is the DDT of when you work out this formula here, then you see that the L acting on F is a very simple formula. It's J equal 1 up to kappa, and then you have then you have your transition rate, Cij, and now what you have to do is you have to just take F at the state xj, and then you have to this is the final state. So this is the final one after the jump, right? And you have to subtract from it what was the initial state. That's the initial state. Okay. And you see, this is sort of computationally. I mean, you will see this in examples which are going to come. I mean, this is computational. This is I'm summing over J. So this is Fi. Okay. So this kind of formulation sort of is computationally easier because you know, all what you have to do is you write down your weight, and then you figure out what is that particular observable you're looking at the final state, and you subtract it from what is the initial state. All right, so this is what I wanted to say on this part. Okay, and so now let me sort of close the generality.
Excuse me?
Yes.
So the evolution operator of the rho of I of function of t, that must be exponential to the power LT transpose.
Yeah. So rho I at time t is well. Okay, I wrote down this formula up here. Right? Yeah, that's right.
That should be T L transpose or just L?
No, this is L transpose. You see. I mean, the probability is it's because of this inversion here. That's why it has to be transposed.
Okay.
You see, when you write down sort of the naive master equation, which you teach your students, then you start with this formula. I mean, you're saying that okay, you know, I have to look at what I'm in the state I have to look at from where I gain and where I lose, right? I mean, but you see, here's Ji and here's Ij.
I see.
So this is why it's the transpose. I will later on. I will always work with the L itself, right? Because it's just much easier. But it's fine, you know. I mean, it's just sort of question of what you're used to, right? I mean, but you will see that the backward is sort of the simpler object. Yes, another question. Okay. Yeah, okay. Sorry, this is too small. Yeah, I realized when writing. Okay. So this I would call is sort of after the jump. I mean, the final. Well, let me write before. No, so this is after the jump. And this is before. I mean, you see, I'm doing a jump from I to J, so this is the state which is sort of after the jump, and this is before the state. Okay, I'm trying to, yes, good, I'm trying to write larger. Okay, so now we come already to the last part of this section, namely, I want to tell you something about the long time behavior, which is very simple, actually. So one of the things, you know, I talked about steady states. I mean, maybe, you know, on that description, maybe I want to understand what's going on for long times. Now, this is sort of quite simple, actually. So this is my space omega of states. And now I divide it into classes points or of states which are connected by transitions, or with non-zero transitions. And so this means that, I'm taking little sections out of this thing, and I call this omega 1. And so omega 1 means that if I start with a state here, then, I can reach any other state through a sequence of positive probabilities. Okay? But, this is sort of maximal. I mean, if I state, it stays always there. I cannot jump over here. So I can clearly partition my omega into these subsets. Now, I mean, very often application, maybe you can reach any other state, but then you see you have a conservation law, then maybe the number of particles is conserved, and then you automatically have such kind of a partition, right? And then the assertion is that if I'm in one of these partitions, I mean, then, if I wait long enough, eventually the system will reach a stationary probability distribution. So now I'm thinking in terms of probability distribution, let's say solving this system, and then you see that when you look at these matrices, I don't want to go into details here, is that eventually you're going to reach some steady state. Okay. Now, of course, the steady state, okay, so let me see, what did I want to say here? Okay, so I have sort of the components. Omega L, I mean, so these are these omega 1, etc., right? And then in omega L, there's unique steady state. And because I'm in a finite system, you have exponential convergence, right? I mean, maybe, one way to think about it is sort of purely algebraically. You see, basically what I'm saying is that this L, so this is my L matrix. I'm just saying that this sort of has a block structure. I mean, this is one thing. You see, there are no transition rates between other ones. I mean, so these things are then sort of zero, right? I mean, so I have maybe a block structure like this, zero, and everywhere else is sort of zero. It just means that, I collected all the states which are connected sort of into this block, and then I have maybe another one which are connected in this block, another one which are connected in this block. And then, if I take the exponential of, if I take e to the LT, then of course out here, there's nothing happening, but here I get sort of the corresponding evolution terms. And so then I'm saying that if I'm looking, at this little part of your matrix, and if I'm waiting long enough, eventually, it will converge, but it will converge to a unique steady state. And of course, the same thing is true for all the other blocks. And the reason why I wanted to emphasize is that I just want to point out that, when you ask the same question for let's say, the systems which I sort of wrote down at the beginning, like, unitary quantum dynamics or classical mechanics, the question of convergence to something, to a steady state is a much more difficult question. I mean, in fact, a question which to some extent is still completely open, right? I mean, of course, empirically, you might observe that if I wait long enough, I mean, nothing is happening. But then going back to a microscopic model and understanding whether this is actually reflected by the microscopic model is typically a very difficult question. I mean, you have to understand chaos, or you have to understand random matrices. It's an ongoing problem, and of course there are many results, but everybody agrees that there's no simple general result like the one over here. So this is one advantage of this stochastic modeling, that this, is sort of usually considered as a very difficult problem, actually can be solved quite simply. Now, you see, I have not, it's just an existence theorem. I have not told you what is I have not told you what is the steady state. I mean, all what you know is the steady state must be, because it's not changing in time, must be a zero eigenvector of the transpose matrix. Okay, so you see, if I still want to know So okay, fine, you converge, but what is it? I mean, at least on that level, you still have to solve an algebraic problem. I mean, you have to a matrix which could be big, and you have to sort of determine what is you know, a zero eigenvector of this matrix. And in the context of concrete problems, I will come back to this. I don't want to do this you know, more generality. Yes.
Yeah. So in the last equation on this side, what do you mean by Fi? F is the observable.
Okay, so maybe my yeah. Okay, so here I see that my notation is maybe a little bit bad. Okay, I use this definition up here. I mean, so I think I should have written this. It's a good point. Yeah. I should sort of switch my notation a little bit to make it incomprehensible. So that's I. Okay, that's after the jump J, and this is I. So yeah, this is a good point. Okay.
Yeah, but what is meant by Fi? Fi is the.
Well, it's just you know, the function. So this is I think of this sort of. I mean, you know, if you think algebraically, this is your matrix, and Fj is sort of a vector. Now I'm looking at this evolution equation. So all the things, of course, are functions of t, right? I'm just writing a matrix equation. ddt of psi of t is equal to a psi of t, right? A is a linear operator acting on psi, and I solve this linear equation, and the solution is e to the at. It's just sort of my notation so that you understand what I'm saying. I mean, if I don't put an index here, then it would be that function at time t equals 0. Right? I mean, so this is sort of the generic setup, right? I just have a linear evolution equation, and which has this kind of evolution, and of course the initial data are not given here. So you know, okay. So maybe I should write psi of 0 is equal to psi. I mean, this is known, and then the unique solution of this equation will be this one here, right? And so I've just written down the same thing over here. I've written it out in components. Fi is sort of, you know, the ith component of that vector. And here's the linear operator acting on Fi, and that is sort of what you have. No?
Yeah, so I don't know what is meant by the vector. So what does the vector F represent?
Well, I mean, F is my observable. I mean, so you see, where did I put it? Well, maybe it's already gone. Okay, so I can just repeat it. I mean, so I take some function F, which goes from omega to r, right? And so this function is F1, etc., all the way up to F kappa, right? I mean, so this observable, because I'm working on a discrete space, these observables are simply represented by kappa vectors. Is that fine? Okay, more questions? Yes?
How can we see that there is exponential convergence to the
Okay, so of course I haven't told you, but you see, basically, okay, so basically what I'm trying to tell you is that I have, okay, so this is something which goes under the name of Perrin-Frobenius theorem. Frobenius, I don't even know how to spell him. Okay, Frobenius. I mean, so basically, you know, once I'm in such a so of course I might have a lot of zeros, but let's look at one block, and let me forget about L. Also, let me just sort of think of this one block, and let me call this matrix A, and then you have a matrix A with the property that Aij. You see, I'm reaching. The assertion is that I can reach any state from any other state through this matrix A. I mean, so this means that A to the n, maybe with a large n, Ij must be strictly positive. I mean, this just means that, you know, if I'm applying this A sufficiently often, I mean, then eventually, you know, I will sort of reach any other point. And then what Perrin-Frobenius tells you is that such a matrix, you know, doesn't have to be symmetric. I mean, any such matrix will have eigenvalues. So it's you know, it is a matrix. Okay. Okay. So yeah. Okay. So the Perrin-Frobenius tells you that you know, asymptotically. Okay. So okay. How should I say this? Okay. So you have one additional information. You know, it's not just a general matrix, but you see it comes. You know, it's a generator of this Markov evolution. So when you look at these matrix elements, okay, so okay, I'm not going to give a sort of complete explanation, but what I want to say is that this theorem tells you that so when you look now at the spectrum of the eigenvalues of this matrix, okay, my assumptions, I mean, for the purpose of these discussions are not complete, but I mean, let's tell you what the final observation is. If I look at the eigenvalues, then of course they can be in the complex plane, but the assertion is that when I look at such an operator, then I will have one eigenvalue which is 1, and then you have sort of other eigenvalues which are sitting over here, and it's you know, if I do it many times, I mean, then it's this eigenvalue which actually dominates, and so that gives you the exponential convergence. Maybe I can explain you a little bit more detail. I mean, I'm not giving a sort of perfect good explanation at the moment, right? But this is what happens.
I did not get why at long times you have to divide plus t to
Why do I have to make such division? Well, because you see, this part doesn't talk to this one. So clearly, you know, if I'm taking a general case, then I will not have a unique probability distribution, right? Because, you know, if I start something which is concentrated over here and over here, then you know, they don't talk to each other. So how could they equilibrate, so to speak? Right? I mean, you see all the states which I'm doing, they are moving in this section, but they never go here, right? And so the general case is that I have to really make this subdivision. And so physically, you know, the way you should think about it is that in the case of the stochastic lattice gases, there I have the number of particles which are conserved. So once I fix the number of particles, which means that I'm sitting in one of these omegas, then, you know, everything sort of equilibrates. But if I take another number of particles, you know, they just don't talk to each other. It's just sort of it's another initial condition, right? Okay, so let's see, I have to look on my watch here. Okay, so where are we? Okay, so now I think I still have sort of 50 minutes. I mean, that should be sort of okay to sort of explain you one other small thing, namely what is just since I emphasize this so much, and maybe I should try to make this distinction. I mean, so what do you in this context? What do you mean by equilibrium, right? I mean, so this is 2.2. Okay, so a priori, this is not so totally obvious, you know, if you sort of come from this sort of somewhat more general framework. But in the community, I mean, there's a complete consensus of how to do it. And so let me explain this to you. And so let me, so now I use now the letter x of t. This is sort of my jump process. I mean, the one which I just explained. Okay. So it's a probability distribution on trajectories. I mean, this is why I call x of t, and they take values in the states 1 up to kappa, right? I mean, so that's the object which I tried to explain you a little bit. And now you want to say, you know, when is this system in equilibrium? Okay, and the traditional answer which you want to use is so. You see, I have at that point it's rather general, and I have not distinguished between, let's say, physically between position and velocities, right? I mean that's something which is an extra point, which I don't want to discuss here because you know, in the models which I'm going to look at, in some sense you only have positional variables, okay? And so I mean, of course that's an important thing, but it would be, you know, sort of leading us too far astray. And so what I want to emphasize is that I want to claim that time reversibility is equal to equilibrium. Well, it's equal to equilibrium. I mean, let me maybe put it this way here, and then there will be a mathematical definition which comes from this time reversibility. So basically, what one is saying is that I prepare the system, and if I see that this system sort of is, you know, if I run the movie forward in time and if I run the movie backwards in time, I would not be able to distinguish statistically, right? So one elementary thing is that you know, you must have, you know, if I look at a single time over here and at some other time over here, you must have the same probability distribution. Okay. So basically what I'm trying to say is I have this x of t jump process, and then I have a steady state, which I just call rho. I mean, so the L transposed on rho must be a zero vector of this. Must be a zero solution of this equation over here. So L must be equal to zero. And at the moment, I'm assuming that everything is connected. So you know, once I give you the weights, I mean, there's a unique rho which satisfies this condition. Okay, and now you want to impose this reversibility, and let me just write it down so that you understand what I want to say by this is that I'm computing the probability of a trajectory, let's say between 0 and t. So I'm not going to write down this probability, but I have told you what the construction would be. And now I want to say that so, you know, I see a particular trajectory. And now I want to say that if I time reverse the trajectory, I say the same probability. So what is the time reverse trajectory? Well, I mean, that's sort of quite clear, right? I mean, I have singled out a time window from 0 up to capital T, and then so maybe I have a jump process which is going this way, right? Now I just run it backwards. Okay, and this is the probability of the x. Well, the running backwards means that I look at t minus t. And again, I mean, you know, this curly bracket means that I'm really looking at one particular trajectory, right? I mean, one given curve. This is sort of what is time reversibility. Okay, so now you know, now there are steps in between which I cannot sort of explain further. But when once you have this definition, then you see that this is mathematically equivalent to what people call detail balance, and that's sort of easier. I mean, I don't have to sort of make arguments in between, but you know, I want to emphasize that you know, the initial definition, what we call equilibrium, is sort of a rather natural definition, right? I mean, if I do a non-equilibrium steady state, I mean, this kind of thing would be not satisfied because there are carbons in the system, and you know, if I reverse, then typically the carbons would also reverse, and so then you know, this would single out the time direction. But if I do the ordinary equilibrium, then you know, it just doesn't single out whether I'm going backwards or forwards in time. Okay, and so when you see that detail balance, I mean, to have sort of physically slightly more intuitive notation, I mean, you see it's a probability, and and it's everywhere. It's positive. I mean, because I have this uniqueness, and so I can write this as e to the like a Boltzmann factor, e to the minus epsilon of j, and I call this energies. I mean, this is sort of, you know, useful for a physicist to think in terms of energies rather than as these probabilities, right? I mean, but you know, you know, it's just, I mean, the epsilon j is minus the logarithm of that rho of j, right? It's not so deep, but it's just sort of convenient to write down the formula, and then the detail balance tells you that if I do a transition from I to j, okay, so the naive conjecture would be that detail, it's time reversible. So maybe, if I interchange I and j, this is just the same. But that's of course too naive. I mean, this is sort of not really what it worked. But the picture is that in terms of energy, I mean, that's sort of the more familiar picture. Maybe I have here another, and then here I have another energy. So I'm sitting in here, and so this is my state I here, and that's my state j, and I'm looking at transitions between those. And of course, the weights will be very different. But if I weight the weights with what is the probability to be in that state, then this identity must make sense. And this is sort of what is implied here by this thing. And so the correct definition is that I have to weight the initial state by rho I, and then if I interchange, of course, here I get the rho j. So this is the detailed balance condition. Okay, and if you want to write it sort of a little bit in a more physical way, I mean, then typically you would say that the Cij. Now you bring this, so to speak, to the other side, and then it looks like an energy difference. So this is e to the minus the epsilon j minus epsilon I, and then I have here. Okay, so this means that the weight from I to j is related to the weight from j to I through this exponential of energy differences. Okay, and that sort of, in that form, this sort of generalizes to many sort of quantities of physical interest. Right? And well, I mean, you see, I mean, when you look at this formula, I mean, then you see that this implies, I mean, you just have to, this is one of these exercises which you have to do, is that once I impose this detailed balance condition, that implies that the L transpose acting on rho is equal to 0, right? I mean, so this is sort of, this is what we wanted to have. It's just sort of, a check once we impose this condition, that in particular we can deduce that this rho j is actually the steady state. Right, and so now why is this important? Well, this. Okay, so I mean, one reason why this is important is that it allows you actually to realize that when you look at the eigenvalues of L under the detailed balance condition, then all the eigenvalues are actually real eigenvalues and on the negative axis. So I think this is sort of the last thing what I wanted to say. Yes?
So this statement of time reversibility for the paths, and then you have this other condition. So the equivalence of this is, I guess, it requires some work, right?
Well, I mean, I don't think it's. I mean, you have to do a little bit of thinking, yeah. But I don't think it's yeah. I mean, yeah.
It's not trivial.
It is. I would not. If you would ask me sort of to immediately sort of write it down on the blackboard, it's sort of, you have to do a little bit of thinking, yeah. But it's like always with these problems. I mean, somehow, if you have the right way of thinking about it, I mean, then that doesn't. It's not so difficult. But yeah, no. But it is somewhat deeper result. Actually, it's something which was first proved by Kolmogorov. I mean, Kolmogorov is the one who sort of understood that. Maybe more in the context of sort of more diffusion processes. I mean, not jump processes, but in some sense, of course, it was understood that the same thing is true for jump processes. Yeah, this is a somewhat deeper result. Yeah. Okay, so let me sort of end with last thing, and then I can take this up next time. So L is a symmetric matrix. So that's nice. I mean, so it has eigenvalues which are, well, so this is not a complete sentence, but I mean, let me just say that what we know about the spectrum. So, you know, under this uniqueness condition, we have an eigenvalue 0. So this is sort of unique. Yeah, I mean, yeah. Okay, and then all the other eigenvalues are here on the negative real axis, right? I mean, so this is what we know sort of in complete generality. And now the point is that, as I emphasized already, it cannot be a symmetric matrix as written. But the point is it's a symmetric matrix in a weighted well, I use Hilbert, but I mean, it's just sort of a linear space here. Finite dimensional space and linear Hilbert space. And so what I mean by this weighted space is that you see, I mean, so usually we have the unweighted space. I mean, let's say Fg would be the summation J equal 1 up to kappa of, I mean, I'm not, you know, in this business, I'm never really looking at complex spaces because our observables are real and L is sort of a real matrix. So let me not worry about this. I mean, that's Fj, Gj. I mean, this would be the usual scalar product between two kappa vectors F and J, right? Now, with respect to this, product, clearly L is not symmetric. I mean, it's just sort of, I make the first example, and it's clear because, you know, I emphasize the I to J is sort of different from J to I, so it cannot be symmetric. Okay. However, I do a little thing. I mean, you know, the question is why this particular scalar product? I could take any other scalar product, but there's one natural scalar product which I denote by Fg, and then I put here an index rho, which I call the weighted one. I mean, so this is J equal 1 up to kappa. And now, so rho is a positive weight, right? I mean, because it's a probability distribution which is strictly positive. So I weight all the states with rho J, and then I put here Fj, Gj. It's just another scalar product. However, when you write out, I mean, so that's another exercise which we can do this afternoon. When I write out the detailed balance condition, then you see the following identity. Now, it's not the flat space, it's the weighted space, and that gives you LF. Okay. And if you just work out the matrix elements, you see that that's exactly the detailed balance. It's just exactly the detailed balance condition as over here. Okay. And so this means that in this weighted space, you know, the L is indeed symmetric, right? I mean, if I take the transpose with respect to rho, then, you know, it will be just to L itself. Now, once I have this identity from this sort of, you know, just sort of standard linear algebra, which certainly I don't have to go into, you know, it will tell you that when I look then at the spectrum of L, I mean, of course, you see L will have, in the flat space, it will have left and right eigenvectors. I mean, because I'm working in the flat space. And when I do a computation, typically, maybe I don't want to involve the rho. I mean, so, but I just want to do, so to speak, in the, you know, this is the flat space. I mean, I just want to do, you know, I just want to look at eigenvalues of the type L. Psi is equal to lambda L psi, right? I mean, that, of course, you know, will have left and right eigenvectors. I mean, that's something which is unavoidable. But because of the symmetry, I still know that the eigenvalues lambda will have the structure as indicated over here. Sorry, this is too much. Okay. All right, but the structure is indicated over here, and then, you know, since there are only finite number of eigenvalues, I mean, there must have a spectral gap, and you can see from this information that, you know, will converge exponentially to the equilibrium state. Yes?
So given a list of coefficients, Cij, is it possible to say, or, you know, without diagonalizing the matrix, whether the steady state will satisfy detailed balance or not?
you mean if you give me L and then you want to know whether
It will give detailed balance or not in steady state.
well, I mean, well, I think okay, that's a good question. Well, okay, so you see, you know, I have yes. I mean, you know, you have a okay. So you know, you have a very precise condition over here. No, I think the answer is yes. I mean, if you give me the weights, you know, then I just assume that there is some rho J for which this detailed balance is satisfied, and then you know, if I can satisfy this equation, I mean, then I'm happy, right? And then typically I can find out explicitly what the rho J's are. But of course, yeah. No, I think the answer is actually yes. I mean, so if you give me weights, then I can sort of check whether they satisfy detailed balance. Yeah.
Kolmogorov loop condition. There is Kolmogorov loop condition.
Well, what the famous theorem of Kolmogorov is that the time reversibility is equivalent to the detailed balance condition.
No, I mean there is this Kolmogorov loop condition, right? So if I take any loop and Cij take the product in the reverse direction, they must be equal.
Well, I think
that's probably that condition. Yeah, that's it. So, yeah. So then, yeah.
Okay, so at least my understanding, so the loop condition is so that they can reach, you know, any state by any others. I mean, that any state can be reached. I mean, any two states can be reached from each other, right? I mean, that's the loop condition.
It's the same as I think this one, like the statement you wrote. Basically, if I take any subset of states and make a sequence of that, and then come back to one, either I get this way or the other
okay.
way.
Now I understand. Okay, so you sort of think about cyclic state. I can go either one direction or the other one direction. Yes, okay, sorry, yeah, that's correct. I mean, here basically, you can think of, you know, what I have written, it's just sort of for a pair of states, but then of course, I can do a loop, and then for each step I apply this condition. Correct, yes. Mm-hmm. Thank you. Okay, I think my time is up, right? Oh, no, I mean, which time did I, at least I started at, okay, so I have to wait for the chairman to, okay, so maybe I just want to say one word, you know, how we continue tomorrow. So I guess I managed more or less how far I wanted to go. I mean, which means that I have explained you detailed balance, and maybe further things. I mean, why don't you ask me, you know, this afternoon a little bit, you know, about this left and right eigenvectors. I mean, that's something which I will, if somebody's interested, I'm happy to explain. And so what I want to do tomorrow is I want to study, you know, those people who are worried that I got too much into formulas. What I want to study tomorrow is a very concrete model, which is called the Voter model, which is a many-body problem, which, however, sort of, you know, you can get without too much efforts, you can get. I mean, which is non-equilibrium, and without too much efforts, you can get interesting behavior. So this will be, I mean, the next topic tomorrow. All right. So thank you very much.